In this video, we are going to look at the chain rule for differentiation. In order for us to remember how to use the chain rule or to learn how to use the chain rule, we must remember composite functions. So our first box here says that the function m is a composite of functions f and g if m of x equals f on the outside and g on the inside, which can also be written f of g of x in this form. Now, the domain of m is the set of all numbers x in the domain of g and all numbers g of x in the domain of f. So let's see if we can roll with this in a few examples. Example 1 says, let f of u be e to the u and g of x be a negative 3x. Find f of g of x and g of f of u. So here it's telling me to substitute g of x into the f of x function on the outside. So let's do that first. F of g of x would have my f function on the outside. So e is going to be the outside function and u is what we put the values in for. And then we're putting g of x in for the u. So g of x is a negative 3x. This winds up giving us, of course, e of e to the negative 3x. That's substituting the g function into the f function. The second function wants us to substitute the f function into the g function. So my outside function is the g function here. So I'm going to write negative 3x, but we're going to replace the x with the f function. So here we will substitute in e to the u. So we wind up having a negative 3 e to the u as my composite function g of f of u. Let's continue reviewing composite functions in example 2. In example 2, it says, write each function as a composite of two simpler functions. So here we're going in reverse. If I were to do this, and I was going to say y equals f of g of x, my outside function would be the 50e to the x. So f of x would be 50 e to the x. Now inside, I would substitute for for x, I would substitute the negative 2x. So that's my g of x function. I use the same variable here, but let's watch how it would work. Here it would tell us my outside function was this. So we would write 50e to the something. And then my inside function is g of x. So that's where we'd put the negative 2x. And that is indeed what they gave us here. Let's look at b. On b, it wants us to decompose the function y equals the cubed root of 1 plus x cubed. I would consider this 1 plus x cubed to be the inside function and the cubed root part to be the outside function. So if we're letting this problem have f as the outside function and g is the inside function, we're going to let g of x be this 1 plus x cubed and f of x be the outside function, which is just the cubed root of something. But since it's in terms of x, we write it this way. If we were to composite them as we were directed, then the outside function would be the cubed root. And in for x, we would substitute the 1 plus x cubed, and that would indeed get us back to where we started. All right, let's look at the power rule using the chain rule. So this is the general power rule if we're using the chain rule. This says that if your function is a composite function, so you have a function on the inside being taken to a power, the way we take its derivative is we multiply this power, n, times the function to the n minus 1, but then times the derivative of the inside function. So let's do an example of that in 3. So we have the derivative of the outside times the derivative of the inside. That's what this means. So in problem number 3, part A, we have f prime of x if f of x is the 3x plus 1 taken to the 4th power. So my outside function is to the 4th power, and the inside function is of 3x plus 1. So finding our derivative here, we'd take the derivative of the power function, which would be 4 times the 3x plus 1 to the 3rd. So that's the derivative of the outside. Then we take the derivative of 3x plus 1, which is simply 3. This will give us 12 times 3x plus 1 cubed. All right, let's look at B. On B, we want to find the derivative of y equals the 5th power of x cubed minus 5. So our derivative will be the derivative of the outside function, which will be our power rule, 5 times x cubed minus 5. We leave that inside part the same to the 4th. Now we take this times the derivative of the inside function. The derivative of this inside function would be 3x squared, and minus 5 would become 0 for that inside function. Cleaning this up, we'd write that the derivative was 15x squared times x cubed minus 5 to the 4th. Let's try C. On C, if we use the power rule, it's kind of confusing to look at it this way. And we could use the quotient rule, but that would be a nightmare. So let's rewrite this function as t squared plus 4 to the negative 2 power. So let's identify this again. So our outside function is this part being taken to the negative 2 power. And the inside function is the t squared plus 4. So the derivative here, it says d dx. This should say dt since it's a t. Excuse me there. Would equal the outside function, the red part. So we do a negative 2 to the negative 3 power. That's the derivative of the outside. We leave the inside the same. Then we'll multiply this by the derivative of my inside function. So the derivative of t squared is 2t, and the derivative of 4 is 0. So it'll just be 2t. Now, if we clean this up, notice we have a negative exponent, and that means that this parenthesis business is really in the denominator. And what's left in the numerator is the negative 2 and 2t. So multiplying these together, we're going to get a negative 4t. And in our denominator, we'll have that t squared plus 4 to the 3rd power. That would be one way to write this a little bit neater. Let's go ahead and look at D. First, if we want to take the derivative of square root, we probably want to write that as a fractional power. So we're going to rewrite g of w as 4 minus w to the 1/2 power. Using our chain rule, it says take the derivative of the outside function. So that will be this part here. Whatever's in there to the 1/2 power. Using the power rule, that'll give us 1/2 to the negative 1/2, because when you subtract your exponents to find the derivative, 1/2 minus 1 is a negative 1/2. Then we have our inside function, which remained the same. Now we take the derivative of the inside function, The derivative of 4 is 0, and the derivative of a negative w is a negative 1. This will wind up giving us a negative value because we have a negative number times two positive numbers. So we'll write negative 1. Now the 2 and the 4 minus w are really in the denominator because this is a negative exponent. So I'm going to write it like this, and 4 minus w to the 1/2. Of course, we could have written this as the square root of 4 minus w. Either way, that is our answer there. Let's continue here with a couple more problems. Here, so here's our general chain rule. If your function m is a composite function, then the derivative is the derivative of the outside times the derivative of the inside, provided that the derivative of the outside and the derivative of the inside exist. Another way to write that is to say that dy dx will equal dy du times du dx, provided that they exist. That's just another way that they like to write derivatives. Let's try this in example 4. So once again, we're looking at inside-outside functions. Here we want to find the derivative in 4a of m of x equals 3x squared plus 1 to the 3/2 power. Let's identify our outside function as whatever's being taken to the 3/2 power, and our inside function would be this part in blue. So our derivative will be the derivative of the 3/2 part. So we take our power rule and say that's 3/2 times this 3x squared plus 1, which stays the same. And if you subtract 1 from 3/2, you're really subtracting 2 over 2, so you're going to get 1/2. Now we take that times the derivative of the blue function, which would be 6x. Cleaning this up, 3 times 6, we're going to multiply this coefficient times the 6x. If you do, you'll get 18x over 2, which is 9x. Then you'll have the 3x squared plus 1 to the 1/2. And you could write that as the square root. Either way is fine. If we look at b, once again, we have a composite function with the e function, e to some power, being our outside function, and then the 2x cubed plus 5 being our inside function. So let's do that again. Our outside function is the e function. Our inside function is the exponent. So as we look at the derivative of our function here, the derivative of an e function is just that same e function. Now the derivative of the inside function, which would be the 2x cubed plus 5, would just be 6x squared. The 5 would become a 0. You could leave it this way, or we could write it as 6x squared being our coefficient times e to the 2x cubed plus 5. Let's have you try problem C. Pause the video, and then we'll go through it together. So we have our outside function being the natural log function, and our inside function being the x squared minus 4x plus 2. Our derivative of a natural log function just tells us to take 1 over the argument. So that x squared minus 4x plus 2 is in the denominator. And then we take that times the derivative of our inside function, which would be the 2x minus 4. Writing that together, we get 2x, this should be a minus, 2x minus 4 over x squared minus 4x plus 2. Let's continue. All right, as the second part of number 4, here we have D, E, and F. I'd like to have you guys try these 3 questions, then we'll go through them together. Pause the video and give them a shot. All right, on D, we can see we have a composite function with 2x cubed plus 4 being all taken to the negative 5 power. Using our power rule for the outside function, we'll get a negative 5 times that 2x cubed plus 4 to the negative 6. That's the derivative of the outside function. Then we multiply that times the derivative of the inside function, which would be, if I'd done this correctly, a 6x squared. Now we have a negative 5 and a 6x, which will remain in the numerator because they are as they are, the 6x squared. So negative 5 times 6x squared is a negative 30x squared. And this 2x cubed plus 4 is to the negative 6 power, so we're in good shape if we throw that in the denominator and put it as the 6th power. So that becomes our derivative. If we look at e, our outside function is the e function, and the inside function is that exponent function. So when we take the derivative of e, we'll have e to the same power that it was, 3x to the 4th plus 6. But then we multiply it by the derivative of our inside function, which would be 12x to the 3rd, and then that 6, when you take its derivative, becomes 0. Multiplying this out, we often would write this as the coefficient of your e function. So you're going to have 12x cubed times e to the 3x to the 4th plus 6. Looking at f, we'll have m of x is the natural log of x squared plus 9x plus 4. So our outside function is the natural log function, and our inside function is that x squared plus 9x plus 4. The derivative of a logarithmic function is to throw the argument in the denominator here. So we have 1 over x squared plus 9x plus 4. But then we take the derivative of the inside function, which will give us 2x plus 9. Cleaning that up, we write it as one fraction. All right, let's try example 5. Move this down. Oh, 5 and 6. Actually, let's save these for the next video, and thanks for watching.